Hey everyone, and welcome to this explainer on the Domain Name System, or DNS. Today, we are literally peeling back the layers of how the internet functions under the hood. We'll start with accessible foundational concepts and then journey all the way down into expert-level network engineering to explore the hidden mechanisms governing performance and security. Let's dive in.
Here is our roadmap for today. We'll start with the Internet's address book, look at recursive versus authoritative servers, dive into the hidden caching layers, and then wrap up with UDP Truncation and securing the whole thing with DNSSEC. Okay, let's get into it.
But before we get into the really technical weeds, I want you to think about something you probably do dozens of times a day. What actually happens the millisecond you type a website name into your browser and hit enter? Well, your browser actually embarks on this invisible, globally distributed journey just to find the exact machine hosting that site. Let's look at how that journey begins.
Section 1. The Internet's Address Book. Separating naming from addressing.
So the fundamental problem DNS solves is pretty straightforward. Computers communicate using numbers, IP addresses, but we humans, we need memorable names. Enter DNS. It's a distributed, hierarchical directory designed back in the 1980s by Paul Mockapetris. You see, early networks used to just share a single static text file called hosts.txt to map names to addresses, literally just a text file. But as networks exploded in size, that manual file became a massive bottleneck. So DNS was built to replace it. Remember, it's just a naming system. It's not the internet itself, and it doesn't carry your actual web page data. It basically just points you in the right direction.
Because DNS is completely distributed, there isn't some giant single database holding every name on the internet. Instead, the responsibility is delegated. First, your browser checks its local memory. If it needs help, it asks a recursive resolver, which starts at the very top, the root server. The root then points it down to a top-level domain server, like .com or .org. And finally, that TLD points to the authoritative server, which hands over the exact IP address. It's basically a highly cooperative baton pass, designed specifically to avoid any single centralized point of failure.
Section 2. Recursive versus authoritative servers. The librarian versus the source of truth.
Now, to really grasp how DNS works, you absolutely have to understand this separation of roles. Think of the recursive resolver as the ultimate librarian. It works on your behalf, tracking down answers by asking other servers. And critically, it stores those answers temporarily in a cache to speed up future requests. On the flip side, the authoritative server is the ultimate source of truth. It's controlled by the domain owner and holds the original definitive zone files. It doesn't go hunting for answers for you. It just provides the facts it officially owns. So the resolvers do all the heavy lifting, while the authoritative servers just hold the definitive data.
And to really give you a sense of the massive scale we're dealing with here, just think of the number 13. There are only 13 logical root server groups globally that anchor this entire hierarchy. It sounds crazy, right? But thanks to a brilliant routing technology called Anycast, those 13 logical IP addresses are actually distributed across hundreds of physical servers all over the world. This ensures that no matter where you're sitting right now, a root server is always close by to kick off that resolution process.
Section 3. The hidden caching layers. How memory banks prevent internet collapse.
Look, without temporary storage, without caching, the sheer volume of global internet traffic would instantly crush those authoritative servers. The mechanism that actually governs this caching is called TTL, or time to live. Every single DNS record comes with a TTL attached to it. It acts as a strict expiration date measured in seconds, dictating exactly how long that record is allowed to stay valid in a cache before the resolver has to go back and ask the authoritative server for a fresh copy. Setting a TTL is actually a highly strategic choice for network administrators. For instance, if you set it to 300 seconds, which is 5 minutes, you can make rapid changes to your infrastructure, but you're forcing resolvers to query your authoritative server pretty frequently. A TTL of 3600 seconds, or an hour, is a really solid balance of speed and freshness. And 86,400 seconds, a full 24 hours, is totally standard for stable, static websites that rarely change. Though it's worth noting that many internet service providers completely ignore TTL values set lower than 300 seconds anyway, just to protect their own network resources. These hidden layers of caching actually operate very differently depending on where you sit in the network. At the browser level, applications have their own incredibly strict rules. Chrome, for example, caches up to 1,000 records for just 1 minute. Just beneath that, your operating system's stub resolver intercepts queries system-wide for all your local apps, and it generally follows standard TTLs. But out on the network, at the ISP or edge level, those servers are managing queries for thousands of users. So to save bandwidth, these massive caches often ignore your carefully planned TTLs entirely, caching records for hours or even days longer than you intended. It's a really fascinating contrast in how data storage is handled at different levels.
Now, if you ever need to bypass all of this entirely, there's the local host file. Located directly on your operating system, this simple text file acts as the ultimate manual override. If you map an IP address to a domain name in the host file, your computer won't even look at its cache or ask a resolver. It just skips the entire DNS process. It's a super powerful tool that network administrators use all the time for testing and troubleshooting.
Okay, here's a fun fact that clears up a massive misconception. TTL countdowns do not reset at each layer. If a resolver holds a record for 10 minutes and then passes it to your computer, it passes along the already decremented TTL value. This is a brilliant design choice because it ensures that caches across the entire internet expire simultaneously. It completely prevents you from getting stuck in an endlessly refreshing loop of stale data.
Section 4. UDP Truncation and Network Transport. The deep mechanics of DNS packets.
To maximize efficiency, DNS was originally built natively on UDP, or the User Datagram Protocol. UDP is lightweight and incredibly fast, precisely because it is stateless. But that 1980s design choice comes with some severe trade-offs. You see, UDP has no positive acknowledgements. It doesn't establish a formal connection state like TCP does. You literally just fire off a packet and hope it arrives. Because it lacks this handshake, UDP is highly vulnerable to source address spoofing, which is something attackers absolutely love to exploit.
Another massive issue with UDP is packet size limits. When a modern data-heavy DNS response is simply too large to fit into a single standard UDP packet, the server won't just chop it up messily. Instead, it uses something called UDP Truncation. The server sets a specific flag, the TC or truncation bit, to 1. This signals the client, hey, this answer is way too big, throw this packet away and re-query me using a reliable high-capacity TCP connection. It's basically the protocol's built-in safety net. But as we know, reality doesn't always play by the rules. A brilliant study by APNIC researchers revealed that some non-compliant resolvers out in the real world see that truncation bit and essentially ignore the safety protocol. Instead of taking the time to set up a new TCP connection, they opportunistically try to use whatever partial data happens to be inside that truncated UDP response. They are literally breaking the rules just to shave off a few milliseconds of latency. Wild, right?
Section 5. Securing DNS with DNSSEC. Protecting the path through cryptography.
Because DNS relies heavily on vulnerable UDP packets and aggressive caching, it definitely has some inherent security gaps. The primary threat we have to defend against here is DNS cache poisoning. Since UDP is stateless, bad actors can bombard a recursive resolver with fake responses. And if they get the timing just right, they can exploit the cache, injecting forged IP addresses. Once that forged record is cached, the resolver will unknowingly redirect thousands of legitimate users straight to malicious websites. It is a devastating man-in-the-middle attack.
So how exactly do we fix a protocol that inherently trusts everyone? Well, the answer is DNSSEC, or Domain Name System Security Extensions. Now, DNSSEC doesn't actually encrypt the data. Instead, it attaches digital cryptographic signatures to the records. First, a zone uses a private key to sign its records. Then, it publishes a public key so resolvers can easily verify that signature. Finally, to ensure no one just swapped the keys on you, a cryptographic chain of trust is established using delegation signer records. This links all the way from the ultimate trust anchor, the root servers, straight down to your specific domain.
When a recursive server fetches a DNSSEC signed record, it computes the hashes. And if those cryptographic hashes do not match perfectly, the server acts like a strict bouncer. It immediately drops the corrupted data and replies to the user with a strict serve-fail error. It intentionally breaks the connection just to protect the end user from being hijacked.
To sum up why all of this really matters, I absolutely love this quote from our source materials. DNS caching affects every website visit. Master DNS cache behavior, and you control one of the internet's most fundamental performance systems. From the very millisecond you hit enter, an invisible web of recursive resolvers, authoritative servers, strict TTL timers, and complex cryptographic signatures are all working together in perfect cooperative harmony.
We've peeled back to layers today, from simple address books all the way to UDP truncation and cryptography.
But knowing just how easily a single poisoned cache or a rogue, non-compliant resolver can alter your entire destination, I want to leave you with this provocative question to ponder. Who truly controls your path through the internet? Thank you so much for joining me for this explainer. Keep learning, stay curious, and we'll see you next time.